Welcome to Lecture 14 of Networks, Friends, Money, and Bytes. Continuing with the last lecture, we're going to talk about the TCP feature of congestion control in the Internet. In order to answer the question, why doesn't the Internet collapse under congestion? Now, we all know we're using more and more bandwidth, and back in Lecture 12, we talked about using pricing as a way to regulate demand and supply. Now, that is over a longer time scale than what we'll be talking about today. Today will be machine level time scale, in fact, very short. We'll be talking about multiples of hundreds of milliseconds. Now, of course, anytime we have demand bigger than supply, whether that is over days, months, and years, or whether that's over milliseconds and seconds, we have a problem. Now, one solution is to increase the supply. The other is to regulate demand. And a great way to regulate demand is through pricing. Back in Lecture 11 and Lecture 12, pricing means real money. Okay, it's your monthly bill at stake. And today, pricing is an interpretation. We're not talking about actually money changing hands among the machines, but it is an interpretation of what's called Lagrange dual variable, or a feedback signal that regulates demand. And this time, we'll see a regulation of demand not only at short time scale, but also over a network with a given topology. So it is a networked distributed regulation of demand. Now, first of all, Internet did collapse back in '86, soon after NSF net came to existence. We observed the first Internet congestion collapse over a 3-hop connection between Lawrence Berkeley Lab and UC Berkeley in California. The data rate normally observed at around 32 kilobits per second, which was pretty good back in '86. Now, of course, 25 plus years later, we cannot possibly tolerate 32 kilobits per second. We often expect 1,000 times faster speed than this. But 25 years ago, 32 kilobits per second was the state of the art. Now, however, that dropped basically 3 orders of magnitude down to about 40 bits per second. That is 40 bits, not kilo, not mega, not giga, but 40 bits per second. That was very slow back even in the 80s. So what went wrong? Basically, what happened is that demand exceeded supply on some of these hops or links for a short while. Now, that should have been just a transient issue. However, TCP runs a connection-oriented end-to-end management. In particular, it uses acknowledgement packets to acknowledge the proper receipt of packets. So if I have a source here and I have a destination somewhere down there going through many hops, the destination would then send back, upon receiving each properly received packets, an acknowledgement packet, okay, shorthanded as ACK. This acknowledgement packet then tells the source that, all right, you got that packet, so you can go ahead and transmit the future packets. If an acknowledgement is not received for a packet, then that packet is resent. So as congestion accumulated on some routers, because the supply, the egress bandwidth, is smaller than the demand, the incoming packets rate, you got accumulation of packets in the buffer. The packets lined up in the buffer has a finite size, and then when it's filled up, all the future packets will be dropped. So this illustrates a 2 megabit per second speed on the egress, and then 1 plus 2, altogether 3 megabit per second incoming. So soon enough, the buffer is filled up, and then the packets are dropped. Of course, these dropped packets never reached destination. and therefore the destination never sends back acknowledgement, and therefore the source never sees that, and therefore all the sources will start resending the packets. And of course, if they keep resending the packets, this demand bigger than supply will persist. This is what we call a positive feedback loop. And basically what we want to do today is to turn it into a negative feedback loop. Instead of reinforcing more and more demand, we should lower the demand so that we don't run into persistent congestion that led to this 3 orders of magnitude drop in the speed. 2 years later, in 1988, Van Jacobson invented the first flavor of TCP congestion control mechanism. Since then, we have seen tons, literally hundreds of variants of TCP, some of which are actually adopted and used today. But before going into any of these specific protocols, let's highlight some principles. Altogether, 5 principles for distributed congestion control in a network. So the goal of this first module of the lecture is to go through this list of 5 principles. Principle number 1. So we're going to run an end-to-end control via negative feedback. This follows the so-called end-to-end principle we talked about last time, that what is best handled by the end host, like your phone or the server on the other end, should be handled by the end host. Now this is not the only way to go, however. For example, in another so-called circuit switching like kind of technology called ATM, it's nothing to do with your bank machine ATM. Okay, this is a network protocol called asynchronous transmission mode. For a period of time, it was a viable competing technology against IP. It eventually did not work out. But during ATM study, people said that certain class called ABR, traffic by ATM, is going to be regulated inside the network rather than be controlled by the end host, specifically by the source based on the feedback helped by the destination. So the first principle adopted by TCP is that congestion control should be regulated at the end host, but you can provide some feedback, some hint to the Homer problem, if you will, to the sources. And these feedback can be inferred metrics from, for example, the presence and the timing of these acknowledgement packets. If you think about it, you really don't have a whole lot of signal to infer about the congestion conditions, except maybe if there is an acknowledgement at all, and if so, when did you receive it relative to the time that you sent the packet. So first principle is end-to-end control, but helped by feedback through the network. Principle number 2 is that we will do this through a so-called sliding window implemented at the source to control the rate. Now, how do you control the rate? Well, one possibility is that you think of rate as a continuum, as water flowing, and then you have a gate to control that. Another is to think of them as discrete packets. And in sliding window mechanism, they have something called a congestion window with a notation of CW and D. So congestion window basically is a buffer zone at the source that says if the congestion window size is 3, you can only send 3 packets at the same time without having acknowledgement. Okay? You can have 3 outstanding packets somewhere out in the network. But in order to send more packets, you need to slide the window forward. And the way to slide the window forward is to receive an acknowledgement. So give me an acknowledgement, I slide the window forward. This is like the mirror image of the similar philosophy of Netflix DVD rental policy, right? You pay the monthly fee, you don't have to return the DVD, but if you don't return the DVD, for example, your Netflix subscription is 3 DVD on your hand at a given time, then you will not get a future DVD if you keep all 3. The moment you return 1 DVD back to Netflix, it will advance the sliding window and you get the next DVD. Okay? You return 1 more or 2 more, you slide one more or two more. Okay, so this is the sliding window. This is a typical picture we draw where we show time axis on the vertical axis and then the transmit buffer here. As time goes on, you see that the window is slided. As it slides more, you get to send more packets. Okay, you send 1 packet, 2 packet, 3 packets. Then you send the 4th packet, the 5th packet, as you get the acknowledgement corresponding to the first 2 packets. All right, sliding window at the source. That's principle number 2. Principle number 3. How do you increase or decrease your transmission rate? In other words, in addition to sliding the congestion window at the source, you can also increase or decrease the congestion window. Increasing or decreasing the window size is not the same as sliding. Sliding simply says I have the same window size. I'm just allowed to slide it forward and start sending more. Increase and decrease says that I can actually change the number of packets I'm allowed to send without having acknowledgement. So increasing, decreasing is like you go to Netflix and say, I want to change my subscription base to go to, say, holding 5 DVD at the same time, holding only 1 DVD at the same time. So how do we increase and how do we decrease? As you can see, window size, CWND, roughly speaking, you can think of that as the transmission rate. Okay? It's a discrete version of transmission rate measured in bits per second. This is packets allowed. Okay? In fact, if you divide congestion or window size by the round trip time and multiply by the average packet size, then you get the average transmission rate. So controlling CWND is equivalent to controlling the transmission rate at the source, that is regulating the demand. The question is how? Well, it turns out that in TCP congestion control, they adopted what's so-called additive increase and multiplicative decrease. Let's look at increase part first. We're going to skip the initialization phase called the slow start. In the homework problem, we'll go through that, and you see that it's actually a misnomer. It should be called low start, but very fast growth. Anyway, we're skipping this. We'll just say that past a certain point, you enter into what's so-called congestion avoidance phase. In congestion avoidance phase, you're going to increase your window size following certain rule. And generally speaking, the rule looks like this. Each time you get an acknowledgement, you get to increase the window size by a number, 1 over the congestion window size. That means over so-called round trip time, RTT, assuming there's nothing getting lost, then you get all CWND packets received and acknowledged properly. And therefore, you multiply these two factors, you see that after each round trip time, you can increase the window size by 1 and advance or slide it by CWND. So this is additive increase. For each constant time, or slightly varying, as we'll see in a minute, due to congestion, the time scale is, say, 50 millisecond, okay, 20 millisecond, 100 millisecond. In that range, you get to increase your window size additively. But when you detect some kind of congestion, upon detection of congestion by inferring based on the timing and the presence of acknowledgement, we'll come to that point in a minute, but assume for the moment somebody can tell you when the congestion started. Upon knowing that, you're going to decrease the window size or the transmission rate, right? That's the whole point here. But when you decrease multiplicatively. You, for example, cut the congestion window size in half. Or in general, you multiply by a certain constant factor. In other words, you reward yourself in a cautious way and you penalize yourself severely. Now, if you actually did it the other way around, you do multiplicative increase and additive decrease, it would be a much more aggressive way to ramp up your transmission speed. Okay, So in the end, people decided to take a cautious viewpoint as you go up your transmission rate before you cut it down when you detect that you've overshot, you've gone too far in increasing the rate. Not only you are fully utilizing capacity, you are over-utilizing the capacity together with some other sources using the same link somewhere in the network. That's principle number 3. Principle number 4 now. Getting back to the question, how do you know? How do you detect congestion? This is actually a very difficult problem. You are trying to do a distributed detection that there is some congestion in the network. Notice, I'm not asking you to tell me where it happens. Okay, you don't have to detect the location of congestion, just whether there is a congestion or not. It's a binary decision, and you're going to infer that by something. Well, as we mentioned, you don't have a whole lot of clues on your hand anyway. You can infer that based on the packet loss or packet delay. So 2 questions. Number 1, loss or delay. Now, loss is a very natural one. If the packet is lost, then you say, gee, there's a congestion. Okay? But it turns out that once packets are getting lost, there's a little delay involved in knowing that information. So by the time you know at the source, it's already been lost for a little while, and that's kind of too late. It's also too much of a binary signal. Okay? Is it lost or is it not lost? As the buffer gets built up, okay, the packets are waiting longer and longer. As they wait longer and longer, you should be able to sense that, because it takes longer and longer for the packets to get acknowledged. So before they are lost, you should be able to measure the delay and use that. So this is a continuous signal rather than a binary one, and it gives you ability to detect and react early enough. We'll see that indeed delay-based at least is a nice supplement, if not a replacement of loss-based congestion control. Second question is it indeed true that packet loss or delay should be viewed as the basis on which you infer congestion? Sounds reasonable, and certainly back in the 80s when the internet was entirely wireline pretty much, that's very reasonable. Okay? But with the proliferation of Wi-Fi and 3G, you see that these wireless links may actually induce a packet loss or delay, not because of congestion, but because of bad channel. For example, a deep fade, okay, somebody standing up, a blockage of the signal, a mobility, and none of that is due to congestion. Okay, it's not because you're sending too fast, it's because you run into a bad channel. So you shouldn't be penalized and back down on your transmission speed. And indeed, there have been many different proposals trying to mitigate this issue in wireless networks. The fifth and the last principle we'll mention in distributed congestion control try to answer the next level of question, which is, all right, loss and delay, very good. I'll use them to infer network congestion, but how do I know them? I have to estimate loss and delay. Remember, nobody is giving me an explicit signal. Nobody signal or control signal or message passing is telling me that, hey, this is link number 5 in Arkansas, and I'm getting too much demand and I'm dropping your packets. And nobody is telling you that, hey, I'm link number 10 and I think you should be transmitting at 2 instead of 3 megabit per second. Explicit signal and message passing is not used in TCPs deployed out there. So you got to make some estimation about the loss and delay. How do you do that? First of all, you got to use timer. Okay? So when you send a packet, you actually timestamp it. So you look at what time is it right now in your clock, and then you record that. By the time you get the acknowledgement back, you look at the time again, and the difference tells you the so-called round trip time we just mentioned, RTT. And you look back into history in the reasonable past. And then you say, what is the RTT that I've been observing? And you pick the smallest such RTT over a period of time, and you call that the minimum RTT. Okay. And then anytime you say that if I'm waiting for acknowledgement, I'm waiting, and I'm dozing off, and I still don't see acknowledgement, then maybe the packet is not just late because it's going through a different route in packet switch network, it's actually lost and it will never give me acknowledgement of that packet. So the question is, how long should you wait? Well, it's a subjective answer. It says, how about 3 times round trip time? That's a belief that, based on traffic analysis from empirical data, that's enough standard deviation away from a normal operation. So you can't keep waiting forever. You got to draw a line somewhere, and the line's typically drawn at 3 times the minimum round trip time. Okay. There's another way to tell, because these acknowledgement not only tell you I got a packet, actually tells you which packet it gets. The way it tells you that is to tell you that the next in sequence packet I'm expecting at this point upon receiving the current packet is whatever, is say 10. That means the last in sequence packet I have received is number 9. All right. Now suppose packet number 10 is lost, but number 11 arrives. So the receiver will send acknowledgement from the destination back to the source saying that I got a packet. Okay? And I'm telling you I'm still waiting for number 10 as the next in sequence packets. So from this you can infer that it must have received a packet later, but not actual packet number 10, but later than number 10. All right? And then say you get 12, packet 12. Okay? And then you send acknowledgement again saying I'm getting a packet, but I'm still waiting for the next in sequence packet number 10. At this point, the source will say, gee, 2 more packets later than 10 have already properly arrived, and yet 10 is still somewhere out there. Maybe 10 is lost. So 3 so-called duplicated sequence number in the acknowledgement. 3 duplicated acknowledgement would lead you as the source to think that maybe it is lost. Okay, so timeout timer plus duplicated acknowledgement will give you a hint that there is a loss. So this is how you calculate delay, and this is how you estimate loss. All right, let's quickly go through these 5 principles again. Principle number 1 says controlling the transmission rate is the job of the source, but as a network you can provide some hint. Number 2 says the source should use a sliding window. Number 3 says when you increase the window size additively, when you decrease it multiplicatively. So cautiously go up, quickly penalize yourself. Principle number 4 says that how do you know there is congestion, and thereby you should penalize yourself? Well, by looking at packet loss and delay. Number 5 says how do you know there is loss or delay? Well, timer difference give you estimate of delay, and timeout or duplicated ACK will give you an estimate of loss. As you can see, the sequence of 5 principles go down from a big picture to specific mechanisms. They all make engineering sense, although you probably can think of alternative designs as well.